probability distribution on the states converges to this unique stationary distribution. But there are some Markov chains where you can get trapped in what's called an ergodic mode. And then there's an entropy rate associated with each of these and so on. It can still be stationary, but you're not going to like it. Because indeed, if you look at a sample function from it, it doesn't really reveal to you what the whole Markov transition matrix looked like. It's only there's a few transient motions that get you into this trap mode, and then you stay within it the rest of the time. Yes? Yeah, Pij is the probability, given that you are in state I, that you go to state J. Yeah, you mean this doesn't look like that?
It looks like the step above the box.
Yeah, yeah. But this step becomes, when I spell out what h of pi is, the elements, see, pi is equal to pi1, pi2, through pim. In other words, the entries here are the Pijs. So that gives you immediately that. Thanks. All right. Now let's do a random walk on a graph. This is an extended example for calculating the entropy rate of a Markov process. So here's a graph. Has a node here, let's say an edge here, an edge here, here, good. Let's do a random walk on it. First of all, it's an undirected graph. Second, when I'm at a node, I pick one of the edges at random. Which in this, I pick one with equal probability. If there are two edges, it's half-half. If there are three, it's a third, a third, a third. And then I go on that edge. And I generate, look, let's see, 1, 2, 3. Well, I don't want to clutter this with names. I generate a random walk on that. Now, what's the entropy rate? I've specified the transition matrix P. What's the stationary distribution? Well, do you really want to solve mu equals mu P if you have, say, 100 states here? Be hard. But let's guess the answer. And that's what someone did many years ago. And they looked at the number of edges coming from here. How many edges here? 3. How many edges? What's the degree of this node? 1. 2, 4, 7, 8. Let's normalize by 8. So these sum to 1. And the guess is that the stationary distribution of node I is the number of edges from node I divided by the summation of EI. Let's call it EJ. because j is a dummy index, which turns out to be ei over twice the number of edges, because I've counted each edge twice. So, I conclude if I do this random walk, and that I spend a fourth of my time here, a fourth of the time here, 3/8 of the time here, and 1/8 of the time here. Notice whenever I get to here, I just go backwards. I go back the next time. I don't have an alternative. So the conditional entropy of the next step, if I'm here, is 0. So, you can prove a number of things. One is this is a time symmetric process. Show P of x1, x2, x3, little values, is equal to P of x3, x2, x1. Just by knowing which nodes I visit in which order, I can't tell the direction of time. But that's a sideshow. Let's not prove that. All right. Let's prove that this is the stationary distribution. So we want to show this satisfies mu I equals summation mu I over Pij. And this is over all I, and this is mu j. The probability of being in node j is the probabilities the time before times the transition probabilities. All right? So, proof. Let's take a look at this. I want to plug this formula in to here and show that it gives me equality. So the first is summation over I of mu I, which is EI over 2E times Pij. Well, some of the nodes I don't go to from node I, so I only go to those that are connected to node I. And I go to those with probability 1 over EI. So I put a 1 over EI for this probability transition. And then I notice that over I over I such that Ij share an edge. Good. Well, this EI cancels, so I get 1 over 2E over summation, and I get a 1 here, over all I such that I connected to J by an edge. But let's look at node J. Here's a node I connected to it. Here's another node I connected to it. Here's another node I prime, I double prime, all connected to J. How many terms in the sum are there? E sub J. So this is E sub J over 2E. And mu sub, right. So, if we plug in mu sub I equals EI over 2E, then we get that the mu I satisfy the stationary equation. All right, here's one remarkable thing here. It doesn't matter how the graph looks, more or less. The number of edges matter. Mu I is a local property. In other words, look at, this is node I, and now I'm going to connect to all sorts of stuff. And I want to know what mu I is. Well, it's just 2 over the twice the number of edges. And the same as if I'd had this thing. And the total number of edges is the same. All right. Last time I asked you to flip a coin on which door you go out of, and then to choose a door at random. Oh, the doors to the outside are locked. Choose a door at random, go in, leave by one of the doors with equal probability, and continue your random walk. So that's a random walk on the graph. This room is a node with 2 edges. The hallway is probably a node with about 12 edges, and so on. And now the question is, how often do you spend in this room? Well, count the number of doors in the building. Say it's 20. 2 times 20 is 40. This room has 2 doors, 2 edges. 2 over 40 is 1 in 20. You'll spend 1/20th of your time back in this room. Right? And I don't care how the other rooms are done. Of course, this is for a connected graph. I don't get to count doors in the room in the building next door or anything like that. They're irrelevant. I can't get there. Okay, what's the entropy rate here? H of this process is summation EI over 2E times log of EJ over all I and J, which are in the set of edges. So I just wrote it up there. Okay. Now, this is of interest. For example, a random walk on a chessboard. A king can move to any of the 8 adjacent squares. But if it's frozen on the edge, it could only 5 possibilities. And if it's in the corner, it only has 3 possibilities. So you'd think that the entropy rate of a king walking on the chessboard is log 8. In other words, 1/8 probability for each of the alternatives. And that's 3 bits. Well,